In example 6.3.1, we have y being uniform in the range from 0 to 1, and we want to find the probability density function for a transformation or a function of y, which is u equal 1 divided by y. I had handed out the list of steps at the beginning of section 6.3 for finding the distribution of some function u based off the method of distribution functions, and I have noted on the side that steps 1 and 2 are mostly necessary for 2 or more y's. So in this situation where we only have one y, I've just rewritten down what steps 3 and 4 were. Step 3 is to find the CDF of u, which is the probability that u is less than or equal to some number little u, and we'll do that by integrating our original PDF for y, f of y, over the region where u is less than or equal to this number little u. And then after we have the CDF, if we want back the PDF, which is our goal, we can take the derivative of that, and then we'll get our little f function. So for the uniform distribution, we know that if you look at the PDF, it's like 1 over theta 2 minus theta 1, and those are 1 and 0 here. So our PDF here is just 1, and that is defined where y is between 0 and 1. So the first step is to look at what is the CDF of u. And so this is, by definition, the probability u is less than or equal to some number little u. And we know that u is equal to 1 over y. So we could write this as the probability that 1 over y is less than or equal to u. And what we need to be working with is y, because we have the function for y. So we could rewrite this as the probability that 1 over u is less than or equal to y. So that's just rearranging this statement to get this statement. So what we're seeing is we need to look at y being greater than or equal to this number. That's just a number. And so what we would do to get that is we would go from that lower bound of 1 over u up to the upper bound, which for our PDF is a 1, and our PDF is 1. And so we would integrate 1 from 1 over u to 1, and this is with respect to our variable, which is now y. So what we get for this when we integrate is just y, evaluated at y equal 1 and 1 over u. So we get 1 minus 1 over u. What we need to note then is also what happens to our bounds. If we end up with 0 less than or equal to y less than or equal to 1, what does that mean for our u? Notice that we're looking at 1 over y. If I can look at 1 over y from the range of 0 to 1, that is going to imply that 1 over y can be anywhere from u to infinity. Okay, so if I just think of where does 1 over y give me when I plug in anything from 0 to 1, I will get anything from 1 to infinity. So we end up with our CDF looking like, remember CDF start off at 0 before we hit the lower bound, so when u is less than 1. And then as soon as we hit the value of 1 and all the way off to infinity, we are capturing our probability by doing 1 over 1 minus u here. So that's our CDF. So we've done step 1 here. Now the next thing is we would take the derivative of this to get our density function. So if we take the derivative of 1 over 1 minus u, what we get is 1 over u squared. So take derivative, and we end up with a PDF of 1 over u squared, because what is this really equal to? This is 1 minus u to the negative 1. So when we take the derivative of this, we end up with a 0 for the derivative of that term, derivative of this term, bring the 1 down and drop the power, so we get u to the negative 2. So we have 1 over u squared, and this is for 1 less than or equal to u, less than infinity, and then we could just say that we're 0 elsewhere or otherwise. So this is the PDF for u, which was 1 over y, where we started with u being uniform, or y being uniform in the range from 0 to 1. You could, if you wanted to make sure this seems valid, make sure this is a valid PDF. So if you would take the integral from 1 to infinity of 1 over u squared du, you should get back a total probability of 1.